in terms of the phase transition. And we could do this for a variety of sizes of nanocrystals and map out the relationship between the size of the nanorod and its phase transition temperature. So we already knew that the bulk form of copper sulfide transitioned from low chalcocite to high chalcocite at 376 Kelvin. And recently, Wang et al. Showed a very slight depression in the phase transition temperature in 70 nanometer nanowires. And all of these black points are data that we took. The inset is a magnification of that. So what you'll notice is that the smallest nanocrystals are transitioning around 310 Kelvin, which is approaching room temperature, but is actually right about where the nanocrystals, where the photovoltaic device is going to be operating. So this means if we have very small nanocrystals in our solar cell, it's probably going to be in a high chalcocite phase. So we have to ask ourselves the question, do we want the nanocrystals to be in a high chalcocite phase? So for that, let's look to the structure and understand what the properties are in relation to the structure. The low chalcocite structure starts with a sulfur sublattice and has copper ions arranged in a very complex pattern around that sulfur sublattice. And that accounts for the very complex diffraction pattern. These vertical lines that are green at the top are the theoretical diffraction pattern from a perfect crystal. And the high chalcocite phase it shares some of these major peaks, but you can see it's a lot simpler. And the reason for that is that as we transition from low to high chalcocite, the very complex ordering of those copper ions becomes amorphous. And this means that we're having a reduction in the electron mobility in our film. It's more difficult for electrons to move in an amorphous material than in a crystalline material. So low chalcocite had relatively high carrier mobility, whereas high chalcocite is going to have relatively low carrier mobility. Additionally, the high chalcocite phase has a lot of ionic mobility because these copper ions are very amorphous. It has high ionic mobility. So neither of these things are good for a photovoltaic cell. It's interesting that this transition it is a solid-solid transition, but it has this strange feature of the copper sublattice melting. So it's kind of a hybrid between a solid-liquid transition and a solid-solid transition. For the purposes of photovoltaics, this study serves as a guideline for what size nanoparticles we should be using if we're going to make copper sulfide nanocrystalline devices. We want to stay above 5 nanometers. But this material might also be useful in a switching application because it's changing by orders of magnitude in its ionic conductivity, and there is some hysteresis, which could give us a window for metastability to be able to switch back and forth and have that on-off state that you need in computing. So to summarize what I've done for the last 4 years, I first succeeded in aligning nanorods on a 1 square centimeter substrate on a variety of device-relevant substrates, and I identified and quantified what those optimal conditions were for alignment. Along the way, I needed to develop a quantification technique so that I could report exactly the number of nanorods that were aligned on that substrate, and this required the derivation of a correction factor. Next, I took these assemblies and cation exchanged them, switching their chemistries to form different types of electrical junctions. Using this platform, we were able to test photovoltaic devices and to identify areas for future work. And finally, I did a study of the size dependence of the important phase transition for photovoltaics from low chalcocite to high chalcocite. So I hope this body of work serves to enable future low-cost and high-performance semiconductor thin films. And I'll open the floor for questions.